All right, so the goal of this video is to define the notion of an ideal of a ring and to give lots and lots of examples. Before we define that notion, though, I'd like to give it some motivation. Why should we care about such a structure? Well, so the main idea is the following. This is what we'll use as our motivation. We can obtain Z mod n from Z by making the identification that any two integers a and b are equivalent if a is congruent to b mod n, meaning that n divides a minus b. More importantly, what we're essentially doing is we're taking the integers n, or rather the integers z, and setting n equal to 0, right? And then kind of exploring the consequences of what happens when I identify n with 0. So the natural question to ask is, can we do this for any ring R? Can I somehow take ring elements, set them equal to 0, and retain a ring structure? And then we'll kind of answer, not in this video, but in future videos, what ring am I actually obtaining? So here are some observations that we'll make that might help motivate the definition of an ideal. So the first thing is, if I look at the set nz, so these are all the multiples of n, these are the elements that become 0 in Z mod n. And specifically, what do I mean? I mean that under the homomorphism f from Z to Z mod n, where I map any integer a to its equivalence class, we have that the equivalence class of a is equal to the equivalence class of 0 if and only if a is a multiple of n. So if and only if a is an element of nz. So these are the elements that become 0 in Z mod n. That's kind of the way we'll talk about this. Another thing we'll notice is that nz is a subring. Another observation is that a is congruent to b mod n, so a and b are being made equivalent to one another, mod n, if and only if n divides a minus b. And that's the same as saying a minus b is a multiple of n, right? N divides a minus b means that a minus b is a multiple of n. So that's just saying that a minus b is an element of nz. And finally, we have one more observation, that if I take an element of nz, call it I, and any other integer, call it a, then I times a is going to be an element of nz. So if I take a multiple of n and multiply it by some integer, I get a multiple of n back. So these properties are going to kind of motivate the next few definitions that we give. Okay, so we're finally ready to define the notion of an ideal using our previous observations as our motivation. So we'll take R to be a ring and I to be a subring of R. We'll call I a left ideal if for every I in I and every R in R, we have R times I is an element of I. So in some sense, the way to think about this is that taking an element of I and multiplying it on the left side by an element of R gives us back an element of I. So left multiplication by elements of R gets absorbed into the ideal. Similarly, we can define a right ideal. So a right ideal is the same kind of, has the same property, but now if I take an element of I and multiply it on the right side by an element of R, the product ends up inside of I. So right multiplication by elements of R gets absorbed into my ideal. And finally, we'll call I an ideal if I is both a left and a right ideal. So if it absorbs elements of R on both sides. In other words, we have that for every I in I and every R in R times I is an element of the ideal, and I times R is an element of the ideal. So we'll refer to this as the absorption property. So I absorbs elements of R. And this is just like observation 4 that we made for NZ just a minute ago. One thing I'll point out is that if R is a commutative ring, then left and right ideals are all just ideals. There's no distinction between left ideals, right ideals, or ideals. And this comes from the fact that I times R is always equal to R times I, right? So the ring is commutative, and I know that I is a subset of R. So I know the elements of I belong to R, so they just commute with elements of R. Another thing I'll note is that some texts, like I mentioned earlier in one of the videos on rings, in particular where we define rings, some texts assume that rings always have identity. We're not making that assumption. In the case where we assume that rings have identity, we also have to assume that subrings have identity. And in that case, we have to assume that I is not a subring, but merely it's non-empty and is closed under subtraction. And we'll see why in a second. We'll see that if a ring has identity and the identity element happens to be in my ideal, then the ideal ends up being the whole ring. So we'll see that it kind of trivializes the definition if we assume under these circumstances that I is a subring. Okay, so let's look at a few examples now. So we'll start off with a kind of trivial example. I'll let R be any ring, and I'll let I be the set containing just the 0 element of R. So it's a 1 element set. And one thing I'll note is that it's pretty trivial to see that I is a subring, right? I is not empty. If I subtract any 2 elements of I end up having to do 0 minus 0. So that ends up being 0. So that's inside of I. And if I multiply any 2 elements of I get, well, 0 times 0 is equal to 0. So I get that it's closed under subtraction and multiplication, right? So it's pretty straightforward to see that I is a subring. Now, to check that it's an ideal, what I need to do is I'll say I have to take an arbitrary element of I. Well, the only element we can choose is 0, and R be an arbitrary element of R, right? Then what do I notice? I notice that R times 0 is equal to 0. So that's inside of I. So I have that I is a left ideal because I'm using left multiplication by R. And I know that 0R times R is equal to 0, which is also an element of I. So I have that I is a right ideal, right? So I could say, hence, I is an ideal. Okay, so this is kind of a trivial example of an ideal. Another example of an ideal is the example we saw in our observations. So let's just check all the details in that observation. So the first thing, I'm going to consider the ring Z, and I'm going to take I to be nz. So it's all the multiples of n for some fixed integer n. Okay, so let's check that this is a subring. Well, the first thing I need to check is I know nz is not empty, since 0 is equal to 0 times n is an element of nz. Okay, so nz is not empty. Now I just have to check that it's closed under subtraction and that it's closed under multiplication, right? So I'll say let a and b be elements of nz. Well, what do I know? I know that then a is equal to n times j and b is equal to n times k for some j and k and z. And then I could take the difference of these two and the product of these two and show that I still end up with a multiple of n. All right, so I could say then a minus b is nj minus nk. So that's equal to n times j minus k. And I know j minus k is an integer, so I've landed inside of nz. And I know if I take a times b, I'm doing nj times nk. And this is simply just n times njk, which is also a multiple of n. So I've landed inside of nz. So I have that this is a subring. And what do I need to check? I need to check the absorption property now. So let's write that down. I'll call this the absorption property. And so what I'm going to do is I'm going to say let I be an element of nz and a be an element of z. And what am I going to do? Well, I know that then I is equal to, let's say, n times t for some t and z. And let's consider I times a. Well, I know I times a is equal to nt times a, which is just n times ta, which is an element of nz. And on top of that, I know that since this is a commutative ring, this is the same as a times I. So I can say, hence, nz is an ideal of z. Okay, so that finishes this example. So another natural example to consider would be let our ring under consideration be the real numbers, and consider the subring Q of rational numbers. What I claim is that I is not an ideal. Right? I already know that Q is a subring. I know that Q is a ring under the same operations as R, and it's a subset of R. But I claim that I is not an ideal. Okay, so how do we prove this? Well, all we have to do is provide a counterexample. I'll say let 1/2 be an element of Q and pi be an element of R. Well, what do I know? I know that then 1/2 times pi, this is going to be pi over 2, is not an element of Q. All right, so the idea is that absorption fails. right? Pi over 2 is irrational. And if I want to check that pi over 2 is irrational, I can do that, right? So let's just check this. If pi over 2 is an element of Q, then pi over 2 is just going to equal a over b for some a and b and z. And these are going to be non-zero. Well, then I know that pi ends up being 2a over b has to be an element of Q. And this is a contradiction because we know that pi is irrational. All right, so this is kind of an easy check. Right? If I assume that pi over 2 is rational, then I arrive at a contradiction, namely, I get the contradiction that pi is rational. We know that pi is not rational. Okay, so the next example we'll consider is the set of matrices of the form AB00, 0, where a and b are real numbers. And I'm going to show that this is a right ideal of M2 of R. Okay, so first let's check that this is actually a subring of M2 of R. So the first thing we'll note is that this set is non-zero since we can produce an element of the set, namely 0, 0, 0, 0 is inside of this set. But we could produce any element. We could do 1, 2, 0, 0 or pi square root of 2, 0, 0, anything like that, as long as we show that there is some element in there. Okay, so the set is not empty. Then what I have to do is show that it's closed under subtraction and show that it's closed under multiplication. So what I'm going to do is I'm going to take two elements, AB00, 0 and CD00, 0 in I. Right, so let's check subtraction. If I subtract these two, I'll get AB00, 0 minus CD00, 0. And this is going to be A minus C, B minus D, 0, 0. And I know that this is an element of I. So it's closed under subtraction. And then finally, I could show that it's closed under multiplication. I'll take AB00, 0 times CD00, 0. And let's see what we end up with. We're going to get AC, AD, 0, 0. And I see that this is an element of I. Okay, so we have that this is a subring. So now let's go ahead and check that this is a right ideal. Okay, so to check that it's a right ideal, what I'm going to do is I'm going to take an element of my ring and an element of my set I, and I'm going to multiply them where the element of I is on the left, the element of my ring is on the right. So I need to take two arbitrary elements. So I'll consider the element AB00, 0 in I, and I'll consider the element CDEF in M2 of R. And so what I need to do is I need to look at AB00, 0 times CDEF and show that I end up with an element of I. So when I do this multiplication, I'll get the first entry is AC plus BE. The second entry is AD plus BF. The next entry is 0, and the next entry is 0. So I see that this is an element of I. Okay, great. So this is a right ideal. One thing I'm going to show also is this is not a left ideal. Right, this is definitely not a left ideal. So how can we show that? Well, all we need to do is produce a counterexample. So I'm going to consider this element, let's say 1, 2, 0, 0 in I, and 1, 1, 1, 1 in M2 of R. So let's consider this element. So I've just taken a second to clean that up. And let's multiply them. So now if I want to show it's not a left ideal, I need to put the element of my ring on the left side and the element of I on the right side and show that I get something that's not an element of I. So when I do this multiplication, I'll get 1, 2, 1, 2. And I see that this is definitely not an element of I, right? So this is an example of an ideal that's a right ideal and not a left ideal. For our purposes, though, in particular, we'll just be worrying about ideals, right? So we won't worry too much about right ideals or left ideals. We're just going to care about ideals in general. So we want the absorption property to hold on both sides. At this point, you might be asking yourself, is there an easier way to check whether or not something is an ideal? Right? One of the things we noticed with subrings was to check that something was a subring, we just had to check that it was not empty, that it was closed under subtraction, and that it was closed under multiplication, right? We called that the subring test. Well, it turns out that there is an ideal test, and it also makes the process for checking whether or not something is an ideal much easier. So what does the ideal test say? Well, we're going to let I be a subset of R, and we'll assume that I is not empty. And we have that I is an ideal if and only if I is closed under subtraction and I has the absorption property of ideals. Okay, so let's prove this statement. So the forward direction follows by definition. There's nothing to prove here. If I know that I is an ideal, then I know it's a subring. Therefore, I know it's closed under subtraction, so 1 holds. And I know that it's an ideal, so it has the absorption property. So the forward direction just holds by definition. The backwards direction is the more interesting one. So I'll say, suppose that I is a subset of R, I is not empty, and properties 1 and 2 hold. Well, one thing we might notice is, well, we already have the absorption property, right? If I want to show that I is an ideal, I need to show that it's a subring and that it has this absorption property. So I know it has the absorption property. And so then I might say, well, all I really need to do is check that I is a subring. So all I need to do is check that it's closed under subtraction and it's closed under multiplication by the subring test. So let's do that. I'll say let A and B be elements of I. Then I know that by property 1, A minus B is an element of I. So we're closed under subtraction. And what else do I know? Well, then I also know that B, it's an element of I, but I is a subset of R. So B is an element of R. And by 2, I get that A times B is an element of I, and B times A is an element of I. But we only need one of these. We don't need to check both. But in any case, I see that it's closed under multiplication, and this completes the proof. So now let's do a few examples of using the ideal test. Our next example is actually going to be pretty important. So this is a definition to remember. So we'll let R and S be rings, and phi from R to S be a ring homomorphism. What I'm going to define is what's called the kernel of phi. And the kernel of phi is just going to be the set of elements R and R, such that phi of R is the 0 element of S. So the set is just the set of things in R that get mapped to 0. Right? So for example, when we considered the homomorphism phi from Z to Z mod n, the kernel of that homomorphism was just all the multiples of n, because every multiple of n got mapped to 0 in Z mod n. Okay, so what I claim is that the kernel of phi is actually an ideal of R, and we're going to see in a few videos that this is a pretty important ideal. Okay, so let's prove this. And how do I prove this? Well, the first thing I might know is that kernel of phi is not empty, since I know that phi of 0 is equal to 0. That's one of our properties of homomorphisms. So 0 is always an element of the kernel. Right? Remember, when I do my subring test, I need to check that the subset that I'm looking at is non-empty. Okay, so I know that the kernel of phi is not empty. Now let's check that it's closed under subtraction. So I'll say let A and B be elements of the kernel of phi. And what I want to do is look at phi of A minus B. So if I look at phi of A minus B, well, I know that this is phi of A minus phi of B. And now, since phi of A, well, since A is in the kernel, I know phi of A is 0. And since B is in the kernel, I know phi of B is 0. So what I'm really looking at here is 0 minus 0. So this is equal to 0. And so I've shown that phi of A minus B is equal to 0. So I can say, thus, A minus B is also in the kernel of phi. Okay, so I've showed that it's closed under subtraction. And then finally, let's show that it's closed, or that it has the absorption property. So what I'm going to do is I'll say let I be an element of my kernel and R be an arbitrary element of my ring. Then let's look at phi of I times R. Well, phi of I times R is phi of I times phi of R, because again, this is a homomorphism. And what do I know? I know that I is in the kernel, so I know that phi of I is equal to 0. So this is going to be 0 times phi of R. And I know 0 times any element of S is going to be 0. And similarly, I can say phi of R times I is equal to phi of R times phi of I. So this is going to be phi of R times 0, because remember, I is in the kernel, so I end up with 0. Right? So I can say, hence, kernel of phi is an ideal. So we'll say it's an ideal of R. Okay, so this is one of our nice important examples, and we'll come back to this in a few videos. Okay, so another really important ideal that we're going to consider is the ideal generated by a set of elements from R. So let's kind of think about this. I'll let R be a commutative ring and A1 through AN be elements of R. And I'll call the ideal generated by A1 through AN. I'm going to use this notation, A1 through AN in parentheses. It'll be the set of elements of the form A1 R1 plus A2 R2 plus dot 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 plus AN Rn, where R1 through Rn are elements of R. So the way to think about this is these are all the linear combinations you can make using A1 through AN, and I'm allowed to use elements of R as my weights for the linear combination. So it's all the R linear combinations of A1 through AN. In particular, if I only want to consider the ideal generated by one element, so let's say the element A1, if I want to consider all the R multiples of A1, I'm going to call this the principal ideal generated by A1. So principal ideal is just an ideal that's generated by one element. Okay, so first thing we need to prove is this thing actually an ideal? Well, let's do that. So my first claim is that this set, I'll call it I just for brevity, the ideal generated by A1 through AN is actually an ideal of R, right? This is actually an ideal. So the name ideal is justified. Okay, so the first thing I'll note is that this set I is not empty because A1 times 0 plus A2 times 0 plus dot 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 plus AN times 0, that's equal to 0. That's an element of I. So I've produced an element of I. Okay, so now I just need to check that it's closed under subtraction and that it has the absorption property. So let's do that. Well, I'm going to first start with two elements of my ideal. So A1 R1 plus dot 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 plus AN Rn and A1 S1 plus dot 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 plus AN Sn. Let them be elements of my ideal, where R1 through Rn and S1 through Sn are elements of R. And what I need to do is I need to subtract these two elements. So I'm going to take their difference, this guy minus this guy. And what do I get when I take their difference? Well, when I do some arithmetic, I get that this is just A1 times R1 minus S1 plus A2 times R2 minus S2 plus all the way up to AN times Rn minus Sn, and then I notice that I have A1 times an element of R plus A2 times an element of R plus so on and so forth plus AN times an element of R. So I've created an element of my ideal and I'm closed under subtraction. I also now need to show that it has the absorption property. And since this is a commutative ring, I only need to show one of the two absorption properties. So let's consider an element of I. So I'll call it A1 R1 plus dot 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 plus AN Rn. And I'll take an arbitrary element little r and R. So now what do I need to do? I need to take the product of these two and show that the product ends up inside of I. So if I take R times this element of I, what do I get? Well, if I do some arithmetic, this is just going to be A1 times RR1 plus A2 times RR2 plus all the way up to AN times RRN. And I see that RR1 is an element of R, RR2 is an element of R, so on and so forth. So what I've done is I've created a R linear combination of A1 through AN, and that's going to be an element of I. So that completes the proof. Okay, and finally, one more definition. If I take a ring R, or a commutative ring in this case, just like above, and I as a subset of R is an ideal, and I'm able to show that I is equal to the ideal generated by A1 through AN for some elements A1 through AN inside of R, we say that I is going to be finitely generated, right? So this is going to be our definition of a finitely generated ideal. In particular, it's generated by finitely many elements of R. So let's look at a few examples of these types of ideals. So I'm going to start with something simple. I'm going to start with my ring is the integers. And what I'm going to do is I'm going to consider the ideal generated by 3. So this is the principal ideal generated by 3. And what is this? Well, this is just the set of multiples of 3 in Z. Right, so it's the set of elements of the form 3R, where R is in Z. And the thing you might notice is, well, we already gave this a name. We called this 3Z. So this is an ideal of Z. Okay, so this is a pretty straightforward example. In general, the idea is that the ideal generated by n is just nz. So we're really just giving nz a new name in the case of the integers. So let's look at a slightly trickier example. So I'll let R be the integers, and I'll consider the ideal I generated by 4 and 6. So let's kind of write out what this set is. These are all elements of the form 4a plus 6b, where a and b are integers. So it's all the linear combinations of 4 and 6, where the weights I'm using are integers. And the thing that I might notice about this is that I can write out some of the elements of this set. So before we begin proving anything, let's write down some example elements of our set and try to figure out what the set actually is, what integers live inside of I. So first thing I might notice is that 0 is inside of I because 0 is 4 times 0 plus 6 times 0. I might notice that 2 is an element of I because 2 is 4 times -1 plus 6 times 1. I'll notice that -2 is inside of I because -2 is 4 times 1 plus 6 times -1. I'll notice that 4 is in the set because I could write 4 as 4 times 1 plus 6 times 0. Similarly, -4 is in the set because -4 is 4 times -1 plus 6 times 0. I'll notice that 6 is in there. I'll notice that -6 is in there. I'll notice that 8 is in there. I'll notice that -8 is in there. And one thing I notice is that I'm able to form all of the even integers, right? If I keep going, I'll be able to form 10, right? 10 is 4 times 1 plus 6 times 1. I'll be able to form -10. I'll be able to form 12. 12 can be written as 4 times 3 plus 6 times 0. I'll be able to form -12. I could just keep going with this. One thing I might also notice is that it's impossible to form an odd integer in this set, right? So there are no odds in this set. And in particular, if k is equal to 4a plus 6b, if this is some element of my set, then I know that k can be written as 2 times 2a plus 3b. So I've just factored out a 2 from 4a plus 6b. And so I see that 2 has to divide k. So in other words, i.e. k is even. Okay, so here's our conjecture. Our conjecture is thus going to be, and we're going to prove this in a second, that I is actually the ideal generated by 2, or that it's equal to 2z, that every multiple of 2 is in the set I. So let's try to prove this conjecture. Okay, so I've taken a second to clean up and to write down our conjecture. So we claim that the ideal generated by 4 and 6 is equal to the ideal generated by 2. So in order to show this, we need to show that 4, 6 is a subset of 2, and that 2 is a subset of 4, 6. So let's do that. So I'll say let k be an element of 4, 6, right? The ideal generated by 4 and 6. Then I know that k is equal to 4a plus 6b for some a and b and z. Well, thus, I know that k, if I factor out a 2, can be written as 2 times 2a plus 3b. So what have I shown? I've shown that k is a multiple of 2. So I know that k is an element of the ideal generated by 2. So what have we shown? We've shown that the ideal generated by 4 and 6 is a subset of the ideal generated by 2. Okay, so we have our subset in one direction. Now we need to go in the other direction. So what I'll do is I'll say, let k be an element of the ideal generated by 2. Here we have to be a little bit more clever, right? Usually when we prove a subset inclusion like this, one direction is easy, one direction is a little bit trickier, and this is kind of the same for if and only if proofs. One direction of an if and only if proof is easier, one is harder. So let's try to do this. How do I do this? Well, one thing I might allude to is the fact that 2 is the greatest common divisor of 4 and 6, right? So I could say since the GCD of 4 and 6 is equal to 2, there exists integers u and v such that for a plus 6, or rather, sorry, for u plus 6v is equal to 2. Okay, and then I could say since k is in the ideal generated by 2, there exists some integer j such that k is equal to 2j. So what I'd like to do now is put these two pieces of information together and show that k is a linear combination of 4 and 6. So how do I do that? Well, what I'm going to do is I'm going to look at this equation up here, this 4u plus 6v is equal to 2, and multiply both sides by j, right? So then I could say then 4uj plus 6vj is equal to 2j, which is equal to k. In other words, k is an element of the ideal generated by 4 and 6. And I could say, okay, so the ideal generated by 2 is now a subset of the ideal generated by 4 and 6, right? And so now I've proved that the subset inclusion goes both ways, right? I've shown that the ideal generated by 4 and 6 is a subset of the ideal generated by 2, and the ideal generated by 2 is a subset of the ideal generated by 4 and 6. So what can I conclude? I can conclude that hence the ideal generated by 4 and 6 is actually equal to the ideal generated by 2. Okay, so we've actually stumbled into something a little bit more general, and I'm going to leave this fact as an exercise because it's actually an instructive exercise. The proof is almost identical to the example we did just now, but the exercise is the following. I'll let R be Z, so it's the ring of integers, and I'll take M and N to be any two integers that are not both 0. And I'll also let D be the greatest common divisor of M and N. And what I claim is that the ideal generated by M and N is the same as the ideal generated by D. So this is a fun exercise worth trying. If you want to try it yourself, follow along with the proof that we just did that showed that the ideal generated by 4 and 6 is the same as the ideal generated by 2. So finally, I'd like to consider one more example of an ideal generated by some elements. So what we're going to do is we're going to assume that R is the ring Z bracket X. So these are polynomials with integer coefficients. And what I'd like to do is consider the ideal generated by X squared and 3. So what is this set? This set is just all polynomials of the form f of x times x squared plus g of x times 3, where f of x and g of x are any two polynomials in Z bracket X. Okay, so I might scratch my head for a little bit and ask myself, well, what exactly am I looking at here? Well, I'll stare at this for a little bit, and I notice that this x squared bumps up my degree by 2. So anytime I look at f of x plus x times x squared, I have a quadratic polynomial or a polynomial of higher degree. So it's a degree 2 or higher polynomial. And then what's controlling the constant term and the coefficient of x? Well, I know that the constant term and coefficient of x is going to be completely determined by g of x times 3. And in particular, I'll notice that the constant term and the coefficient of x is going to be a multiple of 3, because this polynomial here, it only contributes to x squared and higher terms. And so the constant terms have to come from g of x times 3. So I can kind of summarize this neatly. I'll say that I is the set of all polynomials in Z bracket X, whose constant term and coefficient of X are multiples of 3. So that's kind of an interesting example of an ideal. Okay, and finally, I'd like to end with why an ideal, why ideals that contain a multiplicative identity are not terribly interesting. So we have the following theorem, which we'll prove, and the proof is pretty elegant. If R is a ring with identity, so we have a multiplicative identity, and I is a subset of R as an ideal, and the identity element happens to be inside of I, then it turns out that the ideal is equal to all of R, right? So let's prove this. One thing that we know is that I is a subset of R. So it remains to show that R is a subset of I. So what I'm going to do is I'll say let R be an element of R. Well, since 1 is an element of I know that R times 1 has to be an element of I as well, because I absorbs under multiplication. So R times 1, well, that's equal to R. That's an element of I. Hence, R is a subset of I, and so I is equal to R. Okay, so ideals that contain multiplicative identity, not that interesting. As soon as they contain a multiplicative identity, they are the entire ring. This is actually true for any ideal that contains a unit. So you can show that if I contains a unit of R, then I ends up being the entire ring. Okay, and so we'll end with these two exercises. One exercise is the thing that I just mentioned, that if I contains a unit from R, then I equals R. So kind of similar to the proof above. And the second will be that if R is a commutative ring with identity, then R is a field if and only if it has two ideals. Namely, it has the 0 ideal and the entire ring R is an ideal. So fields are commutative rings with identity that have exactly two ideals. So that's a fun exercise to try as well.